Good day, everyone. I am Elaine Sonyas, and our lesson is all about vector spaces. So let us discuss the first topic, which is the vectors in R raised to n. Here are the four objectives. First, represent a vector as a directed line segment. Second, perform basic vector operations in R raised to 2 and represent them graphically. Third, perform basic vector operations in R raised to n. And the last one is write vector as a linear combination of other vectors. Now, let's talk about the vectors in the plane. In physics and engineering, a vector is characterized by two quantities, length and direction, and is represented by a directed line segment. In this chapter, you will see that these are only two special types of vectors. Their geometric representations can help you understand the more general definitions of a vector. Geometrically, a vector in the plane is represented by a directed line segment with its initial point at the origin and its terminal point at x sub 1, x sub 2, as shown in the figure 4.1. So based on the definition of a vector, lagi nating tatandaan na ang vector ay tumutukoy sa mga linya, shape, kurbang linya, at ito ay may direksyon. So now let us look and analyze the figure 4.1 para mas maunawaan natin kung ano nga ba talaga ang vector. Kung maaalala natin way back in high school, napag-aralan na natin yung Cartesian plane and it composed of x and y axis. So yung point na makikita natin dito sa origin, ito yung tinatawag na initial point. Then yung point naman na makikita natin dito, ito yung tinatawag na terminal point. At ang tinutukoy na directed line segment ay itong linya na mula sa initial point, which is in the origin, papunta sa direksyon ng terminal point. The same ordered pair used to represent its terminal point also represent the vector. That is, x is equal to x sub 1, x sub 2. The coordinates x sub 1 and x sub 2 are called the components of the vector x. Two vectors in the plane, u is equal to u sub 1, u sub 2, and v is equal to v sub 1, v sub 2 are equal if and only if u sub 1 is equal to v sub 1 and u sub 2 is equal to v sub 2. Now, let us look at the example 1, vectors in the plane. To represent u is equal to positive 2, positive 3, draw a directed line segment from the origin to the point positive 2 and positive 3 as shown in the figure 4.2a. Next, to represent v is equal to negative 1 and positive 2, draw a directed line segment from the origin to the point negative 1 and positive 2, as shown in the figure 4.2b. So dito sa figure 4.2a, para ma-represent natin yung vector, kailangan natin gumuhit ng directed line segment mula sa initial point papunta sa terminal point. So ang terminal point na tinutukoy ay ang value o components ng vector, which is positive 2 and positive 3. And also, sa figure 4.2b, mula sa initial point, kailangan nating gumuhit ng directed line segment papunta sa terminal point, which is negative 1 and positive 2. Now, let us take a look at the figure 4.3, the vector addition. So kung mapapansin natin, lahat ng vectors, ang directed line segment nila ay nagsimula or dumaan sa initial point or sa origin. Then ang kanilang directed line segment ay mayroong direksyon papunta sa mga terminal point. So para mas maunawaan natin ang figure, let us move on and talk about the vectors operations. Now, let us discuss the vector operations. One basic vector operations is vector addition. To add two vectors in the plane, add their corresponding components. That is, the sum of u and v is the vector. U plus v is equal to the quantity of u sub 1, u sub 2, plus the quantity of v sub 1, v sub 2, is equal to the quantity of u sub 1 plus v sub 1, u sub 2 plus v sub 2. Geometrically, the sum of two vectors in the plane can be represented by the diagonal of a parallelogram having u and v as its adjacent side as shown in figure 4.3. In the next example, one of the vectors you will add is the vector 0 and 0, called the zero vector. The zero vector is denoted by 0. Sa madaling salita, kailangan lamang natin i-add yung corresponding components ng u and v, and yung sum nila ay yun ang magiging vector. So kung mapapansin natin sa figure 4.3, yung may pinakamahabang directed line segment is the vector, at ito yung sum ng vector u and v. And then yung u and v ay ang magiging adjacent sides ng vector. Let us take a look at the example 2, adding two vectors in the plane. The problem is, find the sum of the vectors. For letter A, u is equal to positive 1 and positive 4, v is equal to positive 2 and negative 2, and for letter B, u is equal to positive 3 and negative 2, v is equal to negative 3 and positive 2, and for the letter C, u is equal to positive 2 and positive 1, v is equal to 0 and 0. So let us try to solve the problem. Now, let us try to solve the example 2, adding two vectors in the plane. So, let us add u and v. Substitute for the value of u, positive 1 and positive 4, plus the value of v, which is positive 2 and negative 2. Add their corresponding components. 1 plus 2 is 3, and 4 minus 2 is positive 2. Then for letter B, let us add u and v. Substitute for the value of u, positive 3 and negative 2, plus the value of v, which is negative 3 and positive 2. Add their corresponding components. 3 minus 3 is equal to 0. Then negative 2 plus 2 is equal to 0. For letter C, let us add u and v. Substitute for the value of u, positive 2 and positive 1, plus the value of v, which is 0 and 0. Then add their corresponding components. 2 plus 0 is 2, and 1 plus 0 is 1. The figure 4.4 gives a graphical representations of each sum. Let us take a look at the graphical representation for letter A. So this line is the vector u and its component or value, which is positive 1 and positive 4. And also, this line is the vector of v and its component, which is positive 2 and negative 2. then this line is the sum of u and v, which is positive 3 and positive 2. For letter B, this line is the vector of u with its terminal point positive 3 and negative 2. This line is for the vector of v with its terminal point negative 3 and positive 2, and their sum is at the origin, which is 0 and 0. For letter C, this line is the vector of u with its terminal point positive 2 and positive 1, and the vector of v is at the origin, and the sum of their vector is at the vector of u. Another basic vector operation is scalar multiplication. To multiply a vector v by scalar c, multiply each components of v by c. That is, cv is equal to c times the quantity of v sub 1, v sub 2 is equal to the quantity of cv sub 1, cv sub 2. Recall from chapter 2 that the word scalar is used to mean a real number. Historically, this usage arose from the fact that multiplying a vector by real numbers changes the scale of the vector. For instance, when a vector v is multiplied by 2, the resulting vector 2v is a vector having the same direction as v and twice the length. In general, for a scalar c, the vector cv will be times as long as v. If c is positive, then cv and v have the same direction, and if c is negative, then cv and v have opposite directions. So yung next basic vector operation na gagamitin natin is the scalar multiplication. Ang kailangan lang natin gawin, imumultiply natin yung components ng vector v by the scalar c. Now, let us analyze the figure 4.5. This is the figure 4.5. Kung mapapansin natin, kapag ang scalar c is positive or greater than 0, ang cv and v will have the same direction. And kapag naman ang scalar c is negative or less than 0, the cv and v will have opposite direction. The product of a vector v and the scalar negative 1 is denoted by negative v is equal to negative 1 times v. The negative v is called the negative of v. The difference of u and v is defined as u minus v is equal to u plus negative v. And you can say v is subtracted from u. Let us take a look at the example 3, operations with vectors in the plane. Let v is equal to negative 2 and positive 5. And u is equal to positive 3 and positive 4. The problem is, find each of the following vectors. For letter A, 1/2 times v. For letter B, u minus v. And for letter C, 1/2 times v plus u. Let us try to solve the problems. Let us try to solve the example 3. Operations with vectors in the plane. Let v is equal to negative 2 and positive 5, and u is equal to positive 3 and positive 4. For letter A, 1/2 times v. Copy the 1/2, then substitute the value of v, which is negative 2 and positive 5. Add their corresponding components. 1/2 times negative 2, then 1/2 times positive 5. 1/2 times -2 is equal to -1, and 1/2 times 5 is 5/2. For letter B, we will subtract vector u to vector v. Now substitute. The value of u is +3 and +4 minus the value of v, which is -2 and +5. Subtract their corresponding components. 3 minus -2 is equal to +5, and +4 minus 5 is -1. For letter C, 1/2 times v plus u. Using result of part A, 1/2 times v is equal to -1 and 5/2 plus the value of u, which is +3 and +4. Then add their corresponding components. This is 1, and -1 plus 3 is equal to +2. Then 5/2 plus 4 is equal to 13/2. Figure 4.6 is the graphical representations of each. This line is the vector v, which is -2 and +5, and this line also is half of the vector v, which is -1 and +5/2. And this line is the vector u minus v, which is 5 and -1. So here, this line is the vector u, which is +3 and +4, and this line is 1/2 times v plus u with its terminal point +2 and +13/2. Theorem 4.1, Properties of vector addition and scalar multiplication in the plane. Let u, v, and w be vectors in the plane. Let c and d be scalars. Number 1, u plus v is a vector in the plane. This is a closure under addition. Number 2, u plus v is equal to v plus u. This is a commutative property of addition. Number 3, the quantity of u plus v plus w is equal to u plus the quantity of v plus w. This is an associative property of addition. For number 4, u plus 0 is equal to u. This is an additive identity property. For number 5, u plus -u is equal to 0. This is an additive inverse property. For number 6, cu is a vector in the plane. This is a closure under scalar multiplication. Then for number 7, c times the quantity of u plus v is equal to cu plus cv. So this is a distributive property. Then for number 8, the quantity of c plus d times u is equal to cu plus du, and this is a distributive property also. Then for number 9, c times du is equal to cd times u. This is an associative property of multiplication. Then the last one is 1 times u is equal to 1. Then this is a multiplicative identity property. Next, we are going to discuss the vectors in R raised to n. An ordered n tuple represent a vector in n space. For instance, an ordered triple has the form x sub 1, x sub 2, x sub 3. An ordered quadruple has the form x sub 1, x sub 2, x sub 3, and x sub n. The set of all n tuples is called n space and is denoted by R raised to n. First, R raised to 1 is equal to 1 space and it is a set of all real numbers. Second, R raised to 2 is equal to 2 space and it is a set of all ordered pairs of real numbers. Then R raised to 3 is equal to 3 space and it is set of all ordered triples of real numbers. An n tuple x sub 1, x sub 2, x sub 3, and x sub n can be viewed as a point in R raised to n with the x sub 1s as its coordinate or as a vectors. X is equal to x sub 1, x sub 2, x sub 3, and x sub n. It is the vectors in R raised to n. The sum of two vectors in R raised to n and the scalar multiple of a vector in R raised to n are called the standard operation in R raised to n and are defined as follows. So these are the definitions of vector addition and scalar multiplication in R raised to n. Let U is equal to U sub 1, U sub 2, U sub 3, and U sub n. And V is equal to V sub 1, V sub 2, V sub 3, and V sub n. Be vectors in R raised to n, and let C be our real numbers. Then the sum of U and V is defined as the vector. So U plus V is equal to U sub 1 plus V sub 1, U sub 2 plus V sub 2, U sub 3 plus V sub 3, and U sub n plus V sub n. And the scalar multiple of U by C is defined as the vector. Cu is equal to Cu sub 1, Cu sub 2, Cu sub 3, and Cu sub n. As with 2 space, the negative of a vector in R raised to n is defined as negative U is equal to negative U sub 1, negative U sub 2, negative U sub 3, and negative U sub n. And the difference of two vectors in R raised to n is defined as U minus V is equal to U sub 1 minus V sub 1, U sub 2 minus V sub 2, U sub 3 minus V sub 3, and U sub n minus V sub n. The zero vector in R raised to n is denoted by 0 is equal to 0 and 0. So let us look at the example for vector operations in R raised to n. Let U is equal to negative 1, 0, and positive 1. And V is equal to positive 2, negative 1, and positive 5 in R raised to 3. Find each of the following vectors. For letter A, U plus V. For letter B, 2 times U. And for letter C, V minus 2U. So let us try to solve the problems. Now, let us try to solve the example for vector operations in R raised to n. Let U is equal to negative 1, 0, and positive 1. And V is equal to positive 2, negative 1, and positive 5. For letter A, to add two vectors, add their corresponding components as follow. So u plus v is equal to, substitute the value for u. The value of u is -1, 0, and +1, plus the value of v, which is +2, -1, and +5. Then, we will add their corresponding components. So, -1 plus 2 is equal to +1. Then, 0 plus -1 is equal to -1. And 1 plus 5 is equal to +6. For letter B, 2 times u, to multiply a vector by scalar, multiply each component by the scalar as follow. So we will multiply the value of u to the scalar c. The value of u is -1, 0, and +1. So 2 times -1 is -2. 2 times 0 is equal to 0. And 2 times +1 is 2. Then for letter C, v times 2u, using the result of part B, the value of v is +2, -1, +5. Then we will subtract to the result we get in the letter B, which is -2, 0, and +2. Then we will subtract to their corresponding components. So 2 minus -2, we will get +4. -1 minus 0 is equal to -1. Then 5 minus 2 is equal to +3. Theorem 4.2, Properties of Vector Addition and Scalar Multiplication in R raised to n. Let u, v, and w be vectors in R raised to n, and let c and d be scalars. So number 1, u plus v is a vector in the plane. This is a closure under addition. Number 2, u plus v is equal to v plus u. This is a commutative property of addition. Then number 3, the quantity of u plus v plus w is equal to u plus the quantity of v plus w. This is an associative property of addition. Then number 4, u plus 0 is equal to u. This is an additive identity property. Then number 5, u plus -u is equal to 0. This is an additive identity property. Then for number 6, cu is a vector in R raised to n. This is a closure under scalar multiplication. Then for number 7, c times u plus v is equal to cu plus cv. This is a distributive property. Then for number 8, c plus d times u is equal to cu plus du. This is also a distributive property. Then for number 9, c times du is equal to cd times u. This is an associative property of multiplication. Then the last one is 1 times u is equal to 1. And this is a multiplicative identity property. Now, let's take a look at the example 5, the vector operation in R raised to 4. let u is equal to positive 2, negative 1, positive 5, and 0. V is equal to positive 4, positive 3, positive 1, and negative 1. And W is equal to negative 6, positive 2, 0, and positive 3. Be vectors in R raised to 4. Find x using equation. So for letter A, x is equal to 2u minus the quantity of v plus 3w. Then for letter B, 3 times the quantity of x plus w is equal to 2u minus v plus x. Now, let us try to solve the problems. So let us try to solve the example 5, vector operations in R raised to 4. Let u is equal to 2, negative 1, 5, and 0. V is equal to 4, 3, 1, and negative 1. And W is equal to negative 6, 2, 0, and 3. For letter A, x is equal to 2u minus the quantity of v plus 3w. Using the properties listed in 4.2, we have x is equal to 2u minus v minus 3w. So x is equal to 2 times the value of u, positive 2, negative 1, positive 5, and 0, minus the value of v, which is positive 4, positive 3, positive 1, and negative 1, minus 3 times the value of w, which is negative 6, positive 2, 0, and 3. So x is equal to 2 times 2 is equal to 4. 2 times negative 1 is equals to negative 2. 2 times 5 is equal to 10. And 2 times 0 is equal to 0. Then copy the value of v. 4, 3, 1, and negative 1 minus 3 times negative 6 equals to negative 18. 3 times 2 is equals to 6. 3 times 0 is equal to 0. 3 times 3 is equals to 9. Then x is equals to 4. Then negative 4. And positive 18. Then this will be negative 2, negative 3, and negative 6. This will be positive 10, negative 1, 0, and this will be 0, and positive 1, and negative 9. So let us add them all, or to their corresponding components. So 4 minus 4 is equal to 0. Plus 18 is equals to 18. Then negative 2 plus negative 3 plus negative 6 is equals to negative 11. Then 10 minus 1 plus 0 is equals to positive 9. Then 0 plus 1 minus 9 is equals to negative 8. Then for letter B, begin by solving for x as follows. So, 3 times x is 3x plus 3 times w is equal to 2u minus v plus x. Then we will transpose the x to the left side and the 3w in the right side. So it will be 3x minus x is equal to 2u minus v minus 3w. Then 3x minus x is equal to 2x. Then it is equal to 2u minus v minus 3w. Then we will divide it by 2. Then it is cancelled. X is equal to 1/2 times 2u minus v minus 3w. So using the result for part A, x is equal to 1/2 times 18, negative 11, positive 9, and negative 8. So these are the answer that we get in the letter A. So 1/2 times 18 is equals to 9. 1/2 times negative 11 is negative 11 over 2. Then 1/2 times 9 is equals to 9 over 2. And 1/2 times negative 8 is equals to 4. Theorem 4.3, Properties of Additive Identity and Additive Inverse. Let V be a vector in R raised to n, and let C be a scalar. Then the following properties are true. The first one is, the additive identity is unique. That is, if V plus U is equal to V, then U is equal to 0. Second, the additive inverse of V is unique. That is, if V plus U is equal to 0, then U is equal to negative V. Third, 0 times V is equal to 0. Number 4, if CV is equal to 0, then C is equal to 0 or V is equal to 0. Then the last one is, negative times negative V is equal to V. Next, we will discuss the linear combination of vectors. It is an important type of problem in linear algebra. Involves writing one vector is the sum of scalar multiples of other vectors v sub 1, v sub 2, and v sub n. That is, for scalar c sub 1, c sub 2, and c sub n. X is equal to c sub 1, v sub 1, plus c sub 2, v sub 2, plus c sub n, v sub n. The vector v is called a linear combination of the vectors v sub 1, v sub 2, and v sub n. Let's take a look at example 6, writing a vector as a linear combination of other vectors. Let x is equal to negative 1, negative 2, and negative 2. U is equal to 0, 1, and 4. V is equal to negative 1, 1, and 2. And W is equal to 3, 1, and 2. And R raised to 3 for scalars A, B, and C such that X is equal to AU plus BV plus CW. Write and equate corresponding components so that they form the following system of the linear equation of A, B, and C. Now, let us try to solve the example 6, writing a vector as a linear combination of other vectors. So, our equation is X is equal to AU plus BV plus CW. So, the value of X is negative 1, negative 2, and negative 2. It is equal to A times the value of U, 0, 1, and 4, plus B times the value of V, which is negative 1, 1, and 2, plus C times the value of W, which is 3, 1, and 2. So, A times 0 is equal to 0. Then B times negative 1 is equal to B. And C times 3 is equal to 3C. Then A times 1 is equal to A. B times 1 is equal to B. C times 1 is equal to C. And A times 4 is equal to 4A. And B times 2 is equal to 2B plus C times 2 is equals to 2C. So, the first equation from the first component is negative B plus 3C, and the equation from the second component is A plus B plus C, and the equation from the third component is 4A plus 2B plus 2C. So now, let us try to solve for A, B, and C to get A is equal to 1, B is equal to negative 2, and C is equal to negative 1 as a linear combination of U, V, and W. The first equation from the first component is negative B plus 3C is equal to negative 1. So, negative times the value of B, which is negative 2, plus 3 times the value of C, which is negative 1, is equal to negative 1. Then negative times negative 2 is positive 2. Then 3 times negative 1 is equal to negative 3. It is equal to negative 1. So, 2 minus 3 is equal to negative 1. Then, these are equal. The second equation from the second component is A plus B plus C is equal to negative 2. So, the value of A is 1 plus the value of B is negative 2. And the value of C is negative 1. It is equal to negative 2. So, 1 minus 2 minus 1 is equal to negative 2. So, 1 minus 2 is negative 1. Minus 1 is equal to negative 2. So, these are equal. The third equation from the third component is 4A plus 2B plus 2c is equal to negative 2. So 4 times 1 plus 2 times negative 2 plus 2 times negative 1 is equal to negative 2. Then 4 times 1 is equal to 4. 2 times negative 2 is equal to negative 4. Then 2 times negative 1 is equal to negative 2 equals negative 2. So 4 minus 4 is equal to 0. Minus 2 is equal to 2. Then it is equal.